morning. This is your assignment 6 on contour integration. Let's start. Example 1. Prove that integration from minus infinity to infinity x square over x square plus a square whole square dx is equal to pi over 2a, where a is positive. Now we will integrate fz equal to z square over z square plus a square whole square along the contour C, which consists of this real axis, that is from minus r to plus r, and then it is followed by this semicircle tau from plus r to minus r. This you have to write every time in every solution. Next step, we have to find out the poles. Now here, if you check, you take the denominator equal to 0, and from there you get your poles as z equal to, this is plus minus a iota, right? And because it is having the power 2, that means we are having pole of order 2. So the poles of fz is z equal to plus minus a iota, and clearly fz has double poles, of which z equal to a iota lies inside this contour C. Minus a iota lies outside the circle. Now we have to calculate the residue for this pole, which lies inside the contour, and the residue of the function is, the formula you have to remember, 1 over k minus 1 factorial, where k is 2 here, and limit z tends to a iota, d by dz, how many times you have to derivate? K minus 1 times, that is 2 minus 1, which is only once. Z minus a iota, the power k, k is 2 into f of z, right? So I have already written the value of k over here. So this is 2 minus 1 factorial, it's 1 only, no need to write. And then limit z tends to a iota, d by dz, this is z minus a iota whole square. What is fz? Fz is z square over z square plus a square whole square. So I am splitting up this in factors. So it is z minus a iota whole square and z plus a iota whole square, right? So this is cancelled out with this one, and we are lifting up with, we have to derivate z square over z plus a iota whole square now. And when you derivate this, you will get the derivative of this as 2z z plus a iota minus 2z square over z plus a iota cube. This is equal to, now put the value of z over here, you will get, when unsolved, 1 over 4a iota. So by Cauchy's residue theorem, we get this integration along C, z square over z square plus a square whole square dz is equal to 2 pi iota times the residue, and residue is 1 over 4a iota. Iota, iota cancel 2 with this 4, and you will get pi over 2a, right? Now I have to split this contour into real axis and the semicircle. So this is, real axes are from minus r to plus r, so I'm writing minus r to plus r in terms of x. The function should be in terms of x now. Dx plus along the this semicircle tau, and function is in z, z square plus a square whole square dz. So this is equal to pi over 2a, right? Now I have to calculate this one. Now limit r tends to infinity, if I apply limit r tends to infinity on this integration, z square over z square plus a square whole square dz, this is the formula you have to remember. This is equal to iota times pi minus 0, limit z tends to infinity, z into f of z. So this can be written as pi iota, limit z tends to infinity, z into, now f of z is what? Z square over z square plus a square whole square, right? And because the power of the denominator is greater than the numerator, and because z is also tending to infinity, so if you take z square common and cancel them, then also you will have this as 0. And every time, almost in every problem, this integration along tau comes out to be 0, right? Now, because I need the integration as minus infinity to infinity, right? So I'm letting my r tends to very, very large. So let r tends to infinity in this one. So this is minus infinity to infinity x square over x square plus a square whole square dx plus this is already 0. We have just calculated. This is pi over 2a, right? Here ends up the solution. Now there is an exercise for you. You have to prove that this integration, which is given to you, x square over x square plus a square whole cube dx, this is equal to pi over 8a cube, where a is positive. Everything is same, even the function is also same, only there is a difference in the power. Here the power is 3. That means when you find out your poles, z equal to plus minus a iota, then these poles are of order 3, of which z equal to a iota lies inside the circle, right? Then calculate the residue and then apply the Cauchy residue theorem and you will get your desired result. Next example is, prove that integration minus infinity to infinity x square minus x plus 2 over x to the power 4 plus 10x square plus 9 dx is equal to 5 pi over 12. Now here there are two functions. Let's suppose this to be as your px and this is as your qx. Remember your first remark, whenever such kind of examples come, the degree of this denominator part, the degree of qx, it should be greater than equal to degree of this px plus 2. Is it happening or not? Here degree of qx is 4 and degree of px is 2 and 2 plus 2 is 4. Yes, 4 is greater than equal to 4. So either this degree should be greater than, strictly greater than, or this degree should be equal to the degree of px plus 2, right? So the condition is true, so I'm going to integrate now. So we will integrate f of z in terms of z, the same function, along the contour c, and you have to write again that where c is the contour which consists of this real axis from minus r to r, and then this semicircle tau, which is from plus r to minus r. This you have to write every time. Now this function, can I write it as, I have to find out the factors for this denominator, which comes out to be, this is z square plus 1 and z square plus 9, right? Now to find out the poles, now from here I get the pole as plus minus 1 iota, and from here I am getting the pole as plus minus 3 iota, and these two poles are of order 1, so these are simple poles, right? So clearly fz has simple poles at z equal to plus minus iota and z equal to plus minus 3 iota, of which z equal to iota and 3 iota lies inside the contour, right? So now we have to calculate the residues for both these poles and we have to sum up the residues. So sum of the residues of fz at these poles is equal to, the formula is limit z tends to iota z minus iota f of z plus limit z tends to 3 iota, which is the another pole. So z minus 3 iota into f of z. So this is limit z tends to iota z minus iota. I'm writing my fz to be in the factorized form so that I can cancel this z minus iota. So this is plus 2 over, now here the denominator is having two factors, z square plus 1 and z square plus 9. So I'm writing z square plus 1 as z plus iota and z minus iota. And this is z square plus 9, so that this cancelled with this, plus limit z tends to 3 iota, and here it is z minus 3 iota into f of z is z squared plus z plus 2 divided by, now here there is no need to factorize z square plus 1. I am factorizing this z square plus 9, that is z plus 3 iota and z minus 3 iota. Now these cancelled out with this z minus 3 iota. Now we are lifting up with this. Just put this limit z equal to iota into this and you will be getting it as 1 minus iota over 16 iota, plus if you put limit z tends to 3 iota over here, you will get 7 plus 3 iota over 48 iota. And when you simplify this, you will be getting 5 upon 24 iota. Now I have to apply the Cauchy residue theorem. So this integration is equal to 2 pi iota times the sum of the residues. And the sum of the residues just now I have found to be 5 over 24 iota. So this is 5 over 24 iota. And when you solve, this will be equal to 5 pi over 12. Now taking this contour into two terms as minus r to r along the x-axis, the real axis, changing this z in terms of x now, because this is the integration along the real axis, 10x square plus 9 dx, plus now taking along the contour, this is in z, because x and y both the coordinates are including in z, dz. This is equal to 5 pi over 12. I have to calculate this now, which is equal to iota pi minus 0 limit z tends to infinity, this function, right? So this is iota pi minus 0 is taken to be as iota pi iota, or you can say. And because this limit, the denominator is having greater power than the numerator, and if you tend, z tends to infinity, so this will be 0, of course. Putting this in here, and because I need minus infinity to infinity, so I'm going to let r tending to infinity in 1. So let r tends to infinity in 1, we get minus infinity to infinity x square minus x plus 2 over x to the power 4 plus 10x square plus 9 dx. This is equal to 5 pi over 12, which is the required solution, which we have to prove, right? So here ends up these two expected examples, which are very important. And alright guys, in the next video we are going to do some more examples of different kinds. And one more thing, if anyone wants to enroll my course, Real Analysis and Vector Calculus, you can enroll these courses via the coupons which are provided in the description box. Just go through them. Thank you so much. Have a very good day, blessed day. Goodbye.